Hello guys, and welcome to the long-awaited video on power series. So I'm going to be showing you the solution to three problems that you should probably expect in exam. Three kinds of problems, I mean to say. Now the first one is you're to solve for y prime minus y equal to 0 using power series. The second one is to determine the series solution of the equation d squared y dx squared plus x dy dx plus y equal to 0. And number three is find the power series solution of 1 minus x squared all into d squared y by dx squared minus 5x dy dx minus 3y equal to 0 at x equal to 0. So these are the way the question presents themselves, and you should be able to use one or two techniques that you've learned from power series to solve them. So I'm going to be showing you the technique that is appropriate for each of these problems. Of course, the problems are arranged in order of their difficulty, increasing difficulty. Number one is easy, number two is medium, number three is hard, sort of. But I want to assure you that they are pretty easy, all of them. You just need to grasp the concept and you get it in one go. So let's dive into the solution of the first one with a special method that you'll be interested to learn today. Now, given the first problem, you're given y prime minus y equal to 0, and you want to solve it with power series. So the first thing is that we can actually expect what to see in our answers, because we already know that we can actually solve this differential equation. It's pretty easy. For instance, this is dy dx minus y equal to 0. When you separate variables, you get 1 over y dy is equal to what? Dx. Then if you integrate 1 over y with respect to y and you integrate dx, you're going to get natural logarithm of y is equal to x plus c. Taking the exponential of both sides, exponential in y is equal to exponential x plus c, giving you exponential x times exponential c. Somebody can call exponential c, which is a constant, a, and you leave your exponential x here. So exponential in y gives you y, and y is equal to a exponential x. So the solution to this particular question should give me an exponential of this form, an exponential solution. Okay, so I want to be that after I solve with power series method, the solution that I get should conform to an exponential. So is that going to be the case? So let's find out together. Now, to solve this kind of problem, y prime minus y equal to 0, the method I'm going to recommend is you use this method. You're going to use your y as an infinite series given in this form, a n then x raised to the power of n. This is still a naught plus a1x plus a2x squared plus dot dot dot. Okay, it keeps going like that. So if you're going to use this pattern, the reason why this pattern is okay is because you're dealing with a simple differential equation, linear and homogeneous at the same time. So you could just use this one directly. Now you have y, you also need to obtain y prime, and you now plug it into the solution and you solve, you compare coefficients and you get a pattern, and you know, make your extrapolation from there. You get your answer. So this is how we're going to do it. Okay, first of all, y is given to us as a naught then plus a1x plus a2x squared plus a3x cubed plus a4x4 plus dot 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 plus, let's say, arxr, then plus ar plus 1xr plus 1 plus dot dot dot. It keeps increasing. So this is the pattern. So I'm going to differentiate y prime is equal to differentiating a naught with respect to x. It cancels since it's a constant. Differentiating this one, careful, let's be careful here, let's be careful. So when you differentiate this one with respect to x, you get a1 then plus, you differentiate this one with respect to x, you're going to get 2a2, okay, x. Are we good? And plus, differentiating this one with respect to x, you're going to get 3a3 and x squared plus, you differentiate this one with respect to x, what will you get? Very good, 4a4 and a half x cubed, and it keeps going like that, plus dot dot dot. Then when we differentiate, I will not differentiate this term of course we know what to give us. To give us r a r x r minus 1, but my focus is on this. So when I differentiate it, I'll get r plus 1, then a r plus 1, then x r plus 1 minus 1, which is r. Okay, so it keeps going like that. Now if we examine what we've done so far, we've seen that by differentiating this equation, I've kind of like shifted the differential equation, so that instead of starting from a coefficient a0, it starts from the coefficient a1, and it's actually looking like a series 1 2 3 4 5 6 7 and up to infinity like that. But the most important thing is that we want to solve this differential equation, and the differential equation asks us to subtract y from y prime. So if you do this minus this, you should get 0 in conformance with the differential equation. So the left hand side, this minus this will give me 0, and the right hand side is now going to be what? Capturing, okay, each groups that are similar will subtract themselves. So a1 minus a0 is going to give me a1 minus a0, okay, and plus this minus this, since they are all in x, you can write it as 2a2 minus a1 in x, and plus this minus this can give you what? 3a3 minus what? a2, all in x squared, and plus this minus this can give you 4 minus a3, all in x cubed, and you can keep going. And when you get to this term, this and this, since they have the power and the term x to the r, it will give you r plus 1 ar plus 1 minus ar in x to the r, then plus dot dot dot. Okay, so we can keep going. Sorry, that one is kind of squeezed. So what do you now do with this? So you have to understand that this is still the same thing as you having an x, 0x, and plus 0x squared plus 0x cubed. When you have 0 on the left hand side, it means that all powers of x on that left hand side have the coefficient of 0. So it's still useful for us to start equating each of these coefficients to 0, because on the left hand side they are also going to be 0. That's why the left hand side evaluates to 0 in the first place. So comparing coefficients, we are going to discover that a1 minus a0 is equal to 0. Okay, that's for the constant term. Okay, constant term. So when we compare terms in x, we will find out that, of course, 2a2 minus a1 is also going to be 0, because on the left hand side the coefficient of x is 0. Okay, we can't really see it, but it's 0, is there. Then if we compare terms in x squared, we are going to find out that what? 3 minus a2 is equal to 0. Now if you do it like that, you have x4 to be something like 4a. Is it x4 or okay, x squared, and this x cubed, right? Okay, very good. So you have 4a 4 minus a3 to be what? 0, and so on and so forth. When we get to terms in xr to the r, we're going to get something amazing. So we'll have this, we have r plus 1, then ar plus 1 minus ar, okay, equal to 0. Now this is a special term, and it is called what we know as a recurrence relation. So it gives us a pattern that we can use to develop the relationship between the coefficients of our differential equation. Okay, so or the coefficients of our solution. Now I can still solve this one further. This implies when this equal to this, a1 equal to a0. Okay, so this also implies that a2 is equal to a1 over 2. Okay, when you solve for a2, and you also observe that you can, a1 has been expressed in terms of a0, so this a2 is also a0 over 2. Okay, so this translates to a3 as a2 over 3. a2 is a0 over 2. So when you impress this on this, you superpose this on this, you're going to get a0 all over 3 times 2. So you repeat the same thing, you're going to get for a 4 as a3 divided by 4. And since a3 is a naught all over 3 times 2, when you impress the value of a3 into this, you get a naught all over 4 times 3 times 2. Okay, so we can see a pattern already forming. So we can already see that our AR, okay, plus 1, whatever it is, our AR plus 1 is actually going to be solved as AR divided by R plus 1, okay, AR divided by R plus 1. And if you solve, you get to discover that this is going to give you an A naught all over, you have your R plus 1, you now have your R, and keeps decreasing R minus 1 until you get to 1, and so on and so forth. So what I'm just trying to say is that we have discovered a pattern. Okay, now the pattern can be gotten from your recurrence relation in this case, which if you choose to use, it's fine. But even without the recurrence relation, you've already solved for the first like 4 or 5 terms, including the constant term, and you've discovered that each term can be expressed in terms of the first term, and there's something happening here. I'm seeing like a factorial also. So how do I wrap up my work? I can wrap up my work by saying therefore y is equal to what? A naught plus what? A1x plus A2x squared plus A3x cubed plus A4x4 plus dot 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 plus ARX R plus dot dot dot. Now I've already found the values of each of these coefficients in terms of A naughts. So substituting their values, okay, in terms of A naughts, you have your y is A naught plus A1. We got A1 as A naught over 2. You now have A1 is, oh, A1, sorry, A1 is A naught. Okay, I'm sorry about that. So A1 is A naught. A1 is A naught of x. Okay, then A2, this is where it comes. A2 is A naught over 2. So A2 is A naught over 2x. You have what? Square. Then A3 is A naught over 3 times 2. You now have x cubed. Then A4 is what? A naught over what? 4 times 3 times 2. You have A naught over 4 times 3 times 2. Then you now have x to the 4. It keeps going. Okay, so your AR will be A naught x to the R. Then you now have perhaps R times R minus 1 times dot dot dots up to 1. So, or up to 2 rather. So you can now discover that this pattern, of course the series keeps increasing. R is just like a generalization. This pattern is very familiar and conversant with you. You can see that I can actually factor out A naught from each and every one of these terms, since all terms can be expressed in terms of E naught. You factor it out, you get 1 plus x plus, this is an x squared over 2. Now notice something here. This is an x3 all over 3 times 2, or 3 times 2 times 1. Because you don't see 1 here, there's an invincible 1. This looks to me like a 3 factorial. Is that okay? And plus, this is going to be x4 over 4 times 3 times 2 times 1, which is still 4 factorial. And it keeps going like that. Plus x to the r over r factorial, okay, and plus dot dot dot. So I can see that this is actually conformant with a series that I know. We can recall that our exponential x is defined by the power series m equal to 0 to infinity x raised to the power of m divided by m factorial, okay, which is 1 plus x and plus x squared over 2 factorial. 2 is still 2 factorial plus x cubed over 3 factorial plus dot dot dot. So this whole stuff translates to exponential x. Therefore y is equal to A naught, and the whole of this is what? Exponential x. So A naught is an arbitrary constant. We can call our A naught A. We can call it anything we want. So y is A exponential x, and this conforms to what we actually got earlier up here. Okay, when we solved with the method of variable separable technique, of ordinary differential equations. So you see that this is a simple and straightforward solution to problems like this. So whenever you see a homogeneous linear differential equation and they ask you to solve it with power series, you can use this approach. Okay, introduce y as a power series and then differentiate, substitute differentials into the equation, then compare coefficients to see the relationship between them. Then you now rewrite your solution and look for a pattern. Okay, so that's how we usually solve problems. Even the gigantic Bessel's function was solved using this approach, and the gigantic Frobenius method has this as the foundation technique that it uses to solve differential equation. So this method is very useful. It's one of the most generic method for solving power series solution of differential equations. However, when we get to problem 2 in the next video and problem 3, I'll be introducing us to another method of solving power series solution, which is the Leibniz-Maclaurin method of solving power series of solving differential equation using power series. So I want you to like this video. I hope you learned a lot from it, and subscribe to my channel, hit the notification bell to stay updated, and till the next time we meet, stay blessed. Bye.